Okay, guys, I am recording this section on section 10 2.10. That is the occupancy problem, and I'll start by sharing the PowerPoint presentation. Okay, share application. Hmm, where is it? Just a second, guys. Share application. Now it is here. Okay, this recording will take a little bit of long time because this section is a little bit long. This section is occupancy problem. Again, I'll go into an introduction. What is an occupancy problem here? Throughout this section here, N represents the number of balls, K represents the number of cells or urns or boxes, whatever you will call it. So a typical problem which we are going to discuss in this section is you will be given some N number of balls and you will be given K number of cells. How many different ways you can place these N balls into those K cells? It has wide variety of applications. For example, if you are collecting coupons and if you want to segregate those coupons depending on the types of coupons, you can represent your N as the number of coupons and K represents the types of coupons, and you will sort of categorize them. If you want to list the number of accidents per week, then N represents the number of accidents and K represents the day of the week. So you can have okay, 5 accidents on Sunday and 2 accidents on Monday, like that you can distribute. It has wide variety of applications. Hopefully in the next recording I'll give some of the examples, but in this recording we will discuss how many ways you can do this. Again, this in this particular distribution or number of ways of placing, it makes a very important role that whether you are calling these balls and cells are distinguishable or indistinguishable. For example, in case 1, you are assuming both distinct balls and cells both are distinguishable. In case 2, balls are indistinguishable and cells are distinguishable. In case 3, balls are distinguishable and cells are indistinguishable. In case 4, both are indistinguishable. So in case 1, both are distinguishable. In case 4, both are indistinguishable, and all the different options are in the middle. And each case can be further subdivided into 2 categories, whether you want those cells to be empty or you don't want any of the cells to be empty. So those are 4 bigger cases, and each bigger case has 2 sub cases in the middle. Okay, I will start with an example. Let us start with case 1. Here in this case, both balls and cells are distinguishable. That means you can treat them separately. So case 1a, my cells can be empty. Let us start with a simple example. There are suppose 2 balls A and B, and there are suppose 3 different cells or urns or boxes. How many different ways you can distribute them in these boxes? How many different ways of you can arrange it? And here both balls are different. You can assume one is red, the other is blue, and all the boxes or the cells are different. You can assume they are of different color as well. So that is my pen. Here these represents say cells. I have 3 different cells and 2 balls. Here my cells can be empty, so I can both the balls in the first cell, or I can put both the balls in the second, or I can put both in the third. So this is one distribution, this is one distribution, this is one way I can distribute. Or I can put one in one and two in two, or one in this and this in here. So these are another 3 ways I can distribute. Or since the balls are different, keeping A on the first and B on the second is different from B on the first and A on the second. With the same logic, B on the first and A on the third is different from A on the first and B on the third, and this is different from this. So there are total 9 different distributions. So I can distribute 2 balls in 3 cells if everything is distinguishable in 9 different ways. This you can simply think of that as a product formula if I want to generalize this. There are n balls. In this case, n is going to be in this case n is going to be 2, and k choices of cells for each ball. So first ball I can put in k different cells, and the second ball I can put in k different cells. In the third ball I can put in k different cells. So I'm multiplying k n number of times. This is by the product rule. So if you look into the top example, k is going to be 3 and n is going to be 2. So there are 9 different ways I can distribute. You can see for each ball there are k different choices I can put. So that is product rule, k power n. Let us look at one more example. Now suppose here n is 2 and k is also 2. Then how many number of ways you can distribute 2 distinguishable balls and 2 distinguishable cells? If I use the formula, that is simply going to be k power n, that is 2 square, that is going to be 4. It is as simple as that. If you want to list all of them, you can list it like this. I have 2 cells and I can put both the balls in the first cell or in the second cell. I can put first in the first one, 2 in the second one, and this in this one, and this in this one. So these are 4 different distributions. So again, we have the general formula and also how to list each of them. So case 1A is completely done. Now suppose you don't want any cell to be empty. That means you don't want distribution 1 or distribution 2. You don't want any of the cells to be empty. Then how to do that? That is case 1B. Suppose n is 2. N is the number of balls as I mentioned, and k is 3. Since there are more cells than balls, certainly at least one of the cell has to be empty. Even if you place one ball in each cell, one is going to be empty. So it is not possible. So whenever you want case 1B to be, then you always want, where is my pen? Then you always want number of balls to be more than the number of cells. So n is always have to be bigger than or equal to k. Then only this is possible. So example 3 is not going to work. If n is 2 and k is 2, then there is only 2 options. I can put one in first cell and second in the second cell, or this. So the answer is only 2 ways I can do this. Two ways I can do this. That means if you go to example 2, the distribution 1 and 2 are not possible. Only distributions 3 and 4 are possible. And is there a general formula for this? Yes, there is a general formula how to come up with this. But I will come to this after covering some of the other cases, because the formula we will be deriving in those will be useful in here. So let us take a break for case 1B. Now go to case 2. Okay guys, if I'm going too quickly, please let me know. Here in this case, indistinguishable balls and distinguishable cells. That means I see no difference between the balls. That means all the balls are of the same color and size, and the cells are different. Let us look at one example. The number of ways I can put 2 indistinguishable balls to 3 distinguishable cells. I mean, cells are different, and I'm assuming all the balls are the same thing. Say for example, cells are different, 1, 2, 3. I can put both the balls in the first one, or the second one, or the third one, or I can put in these two, or these two, or these two. Certainly Now you are not going to have AB or BA here because both the balls are indistinguishable. So there are only 6 ways I can do this. Now, this Nast theorem will give us general formula how to come up with this. The number of ways I can distribute n indistinguishable balls into k distinguishable cells is given by this formula. I will prove this theorem with the help of this example, then we are going to prove in general in the next slide. Here, if you take this example, I am calling, there are 3 cells. So I will call these cells as C1, C2 and C3. There are 3 cells. If you have 5 cells, you will call C1 to C5. There are 10, C1 to C10. Now, if you take this distribution 1, there are 6 different distributions, right? 1, 2, 3, 4, 5, 6. Here, I will call distribution 1 as, I am placing both the balls in the first cell, so C1 comma C1. And say distribution 3, if you take both the balls in the third, so it is C3 comma C3. If you take distribution 5, I am placing one ball in cell 1 and one ball in cell 3. For example, distribution 6, I can think of that as one ball in cell 2, the other is in cell 3. So here, if you think a distribution is nothing but you are simply saying you are listing each ball into the cell in which you are placing it. For example, cell 1 I'm putting the first ball, cell 1 I'm putting the second ball, cell 3 I'm putting the first ball, cell 3 I'm putting the second ball. So each distribution is nothing but is simply a listing for each ball into the cell you are placing. That means each distribution, in this case, I'm simply selecting 2 members out of these 3 members. That's what I'm doing. So each distribution in this case is nothing but selecting 2 things because the number of balls is 2. That means each distribution is selecting 2 things out of these 3 things in which repetition is allowed, and I don't care about the order. If you have seen the previous video, that is nothing but combination, repeated combination, and you are picking, there is a 3 set, that is C1, C2, C3, and you are picking 2 things out of 3 things. That is C power R 3 comma 2. So each distribution is nothing but selecting of n cells out of these k cells. Repetition is allowed. That is the reason C power R kn. So according to this, that is going to be 3 plus 2 minus 1 comma 2. That is going to be C4 comma 2. If you use the formula, you are going to get 6. Because that is 4 factorial over 2 factorial times 2 factorial. That is going to be 6. So that is the proof for this theorem. Now I'm going to generalize this. I explained this with the help of this example. Hope that made some sense. Now let us generalize this. The number of ways to distribute undistinguishable balls into k distinguishable cells is this. So here, please remember, all the n balls are indistinguishable. All are of the same thing, and k cells are different. You are remembering the k cells as C1 to Ck. That is the same thing like in the previous example, C1 to C3. A distribution of n balls is summarized by listing for each ball the cell into which it goes. That means if you look at distribution 5 is C1 comma C3, you're listing the cell into which that particular ball goes. So a distribution is simply a collection of n cells out of k cells, really. So the number of ways of distributions, or the number of different ways, is nothing but the number of ways I can select n items out of k items, that is n balls out of k cells, in which the repetition is allowed, and I don't care about the order. So that is the reason it is a combination. So that is given by this formula, and that is nothing but this. That is what we proved in the previous section. So if you have seen the previous recording, this might have ring some bells already. And we proved this with the help of this example also. So that is this theorem. Again, in this case, as I mentioned, you are assuming and you are allowing One of the cells can be empty or more than one can be empty. If you don't want your cells to be empty, then you are going to go into the next case. Now you have n indistinguishable balls and k distinguishable cells. Now you don't want any of the cells to be empty. When n is 2 and k is 3, that means there are more cells than balls. As I discussed previously, that is not possible, because at least one will be empty because there is more cells than the balls. Now let us look at this example. This is the way we'll prove the result. Suppose there are 5 balls and all are the same. So I am calling all of them as A, and there are 3 cells. How many ways you can distribute? And you don't want any cell to be empty. So the way you need to do that is, there are 3 cells, 1 cell, 2 cell and 3 cell. First you put 1 ball in each. So 3 are already taken care of. Now there are 2 balls left. So 2 balls left. And there are 3 cells left. Now you need to figure out how many different ways I can put these 2 balls into these 3 cells. Now I don't have any restriction because I already filled each cell. So the number of ways I can put 2 indistinguishable balls into 3 distinguishable cells. That is exactly same as the previous example, example number 8. That is exactly, sorry, I apologize, I went to the next one. That is exactly same as this example. Number of ways you can put 2 balls in 3 cells. And I know that can be done in 6 ways. So this can be done in 6 different ways. That is C power R, C power R 3, 2. That is done in 6 different ways. So you will put 1 in each ball, and then so the final answer is 6. So that is the general formula. So the number of ways I can distribute n indistinguishable balls into k distinguishable cells is given by this formula. The formula derivation is extremely simple. Here you are always assuming n is bigger than or equal to k, otherwise you can't do this. This is extremely informal proof. So first, place 1 ball in each cell. So k balls are taken care of. Now there are only n minus k indistinguishable balls, because k balls out of n balls are already taken care of. Now there are only n minus k of them are remaining. Hope you can understand my handwriting here. Now we need to place these n minus k indistinguishable balls into k distinguishable cells. Now I have no restriction because I already placed 1 in each. Now all the cells I know are not empty. And this can be done in by theorem 2.4 in this many ways. And now how many, apologize, just a sec, and this can be done in and k cells and in n minus k balls, right? So this can be done in this many ways. This is going to be by the previous result in the previous section. This can be done in this plus this minus 1, comma n minus k. If you simplify that, k's will cancel out. So this is n minus 1 comma n minus k. But if you remember, I don't know how many of you remember this. This result, we have this result. Maybe I will write here. Hope you apologize for that. This is C of n r is going to be C of n comma n minus r, that we had seen in permutations and combinations. So this is exactly same as C of n minus 1 comma this minus this. N is going to be n minus 1, r is going to be n minus k. So here n's will cancel out and you will end up getting n minus 1 comma k minus 1. Because n's will cancel out and minus will become plus k. So that is going to be your final proof. So in this particular example, if you want to use the formula, n is going to be 5 and k is going to be 3. The number of ways I can do this is n minus 1 comma k minus 1, 4 comma 2. So 4 factorial over 2 factorial times 4 minus 2 factorial. If you simplify, you will get answer as x. Again, this proof, if you cannot read my handwriting, please go to page number 54 on the textbook and you will see this result. Page number 54. So this is case 2b. So now we have formula for case 2b as well. Now let us go to case 3. Now in this case, balls are distinguishable and the cells are indistinguishable. That means there are 2 balls and 3 cells. Let us take an example. Now cells can be empty. Now, so balls are distinguishable, so I'll call AB, and cells are all same, so I'll call 1, 1, 1. So if you look into example 1, if you assume cells are indistinguishable, for example, then all cells are the same thing. Suppose assume cells are distinguishable. So cells are say 1, 2, 3, and we had seen from example 1 there are 9 different distributions. Now if you assume all the cells are same, these distributions 1, 2, and 3 all are equal to each other. So you will have only one of these. You can remove the others. All are same because all the cells are same. Now these things, since all the cells are same, either AB here or AB here or AB here or BA here or BA here, BA here, all are same thing. So these 6 distributions are same as 1. So these 6 will become simply 1. So now there are only 2 different distributions. So your final answer is simply 2. So what those two balls in what's with one cell and none in the others? That is what these 3 represents. And 2 cells with 1 ball in each and 1 is being empty. That is what this represents. So there are only 2 different distributions if you assume all the cells are the same thing. You assume all the cells are the same thing. So now if you assume all the balls are different and the cells are same, and the final answer is only 2 in this particular case, where n is 2 and k is 3. Is there a general formula for this? Yes, there is one. I will come to that in the next slide after covering case 3b. So in case 3a, my cells can be empty. Now if I don't want any of the cells to be empty, when n is 2 and k is 3, the exact same as previous example. Now I don't want any of my cells to be empty. Now you know that is not possible because there are more cells than balls. So whenever your cells cannot be empty, you always want to make sure number of balls are at least more than or equal to the number of cells. When n is 2 and k is 2, now there are 2 cells and 2 balls. So 2 cells and 2 balls. Now the only way I can do this is, because I don't want any of my cells to be empty, I need to place one cell, one ball in one cell and the other ball in one cell. That's it, because both the cells are same. AB or BA are exactly the same thing for me. So there is only one way I can do this. So the answer is 1 here. So there is a formula for this, and that formula is called the Stirling number of the second kind. The number of ways I can put n distinguishable balls into k indistinguishable cells with no cell being empty is given by this number. And this number is a very complicated number, and the proof is beyond the scope of the book. After looking at the formula, I know you will appreciate me not writing the proof for it. The formula is going to be this. Here n represents the k factorial summation that I is going from 0 to k, negative 1 to the I. This is k choose I, k minus I power n. This ugly looking thing is the formula. Again, this is there on page 54 of the textbook. Please, if you have the textbook, go to that. Here, this symbolism is nothing but C of k comma I. This is combination. So the formula is k factorial. Instead of C, k comma I, they use this symbol. So both are the same thing. So in the above example, if you want to see S of 2 comma 2, and you know the answer is 1, there is only one way you can do that. So in this case, 1 over 2 factorial, the symbolism, I is going from 0 to 2, negative 1 to 0, 3 choose 0, 3 minus 0 power n is going to be 2, plus negative 1 power 1, 3 choose 1, this one plus negative 1 square. See, I is running from 0 to k, right? K is in this case is going to be 2. So k is, I apologize, in this case k is 2. I keep writing 3 here. I'm so sorry guys, this is simply 2, please remember. So 1 over 2 factorial is 1 over 2, negative 1 power 0 is simply 1, and 2 choose 0, that is going to be 2 minus 0 factorial, that is simply 1, and so that becomes 2 square, and negative 1 power 1 is negative, and 2 choose 1, if you use that, that is going to be 2, and 2 minus 1 is 1 square, and 2 minus 2, that is simply going to be 0. So if you do this math, you will get your answer as 1. So this is the complicated formula. The formula is beyond the scope of the book. So this is called the Stirling number of the second kind. Again, since you are not remembering any of the formulas anyway, so but I think it is very easy for you to understand just by working with examples rather than working with the formula, because formula is a little bit complicated. But this formula is useful when n and k are really a little bit bigger numbers, because at that time you cannot write all the distributions. So this is the formula for case 3b when the cells cannot be empty. Now we are going to derive formula for case 3a when the cells can be empty. And again, at that number of ways I can put n distinguishable balls into k indistinguishable cells with the cells being empty is going to be given by this formula. Again, they simply said in the textbook the proof is beyond and complicated. The one way you can understand is you have to use a addition principle. This is simply saying how many ways I can put n distinguishable balls in k distinguishable cells with no cell being empty, that is this, or n balls into k indistinguishable cells with one cell being empty, and with two cells being not empty, with three cells being not empty, and you will add all the possible combinations, you will get this. So for example, when n equals to 2 and k equals to 3, the number of ways I can do that, in this case we already got from the previous example as 2 different ways. If you want to use the formula, that is simply going to be s of n1 plus s of n2, and you go up to s of nk, k is going to be 3. And for each of these S of n1, you use this ugly formula in the previous section and you calculate, which I'm too lazy to do it. You should get your final answer as 2. In this case, n is going to be 2. So this is S of 2, 1, S of 2, 2, plus S of 2, 3. You should get your answer as 2. So again, the proof is beyond the scope of the book, so I don't want to waste your time by going through more explanation here. Now, this S of nk we defined just now is useful in coming up with the formula for case 1b, which I left it. So I'm going to go back to case 1b and talk about it. This is case 1a, where the balls and cells, everything is distinguishable. How many ways you can put n balls in k cells and they can be empty? That is simply the product rule. And we had seen all this. Now, if the cells cannot be empty and everything is distinguishable, when n is 2, k is 3, we said that is not possible. When both are equal to each other, and I mentioned there are two ways you can do this. I can put first ball in one and second ball in this, or the other way. The formula for this is simply going to be, so the way you need to do that is, first assume cells are going to be indistinguishable. That means you have n balls and k cells. Now if you assume cells are indistinguishable and no cells being empty, and that can be done in S and K ways. So S and K is the number of ways we can put n distinguishable balls. I'm sorry, you can understand my handwriting there. In K indistinguishable cells. So assume initially all the cells are the same thing and you arrange them. Then number the cells as 1 to k. Number the cells as, now you are giving them a number. That means now you are distinguishing between them, and you see how many ways they can arrange among themselves, and they can arrange among themselves in k factorial ways. So by product rule you get the above answer. Again, this explanation is there on page 55. So for our example, we know that there are two ways you can do this. So here n is 2 and k is 2, that is simply 2 factorial times s of 2 comma 2, that is 2 times 1, that is going to be 2. Okay guys, so that is case 1b. Now I'm going to go to the last case, that is case 4. Now all the cells and balls, everything is indistinguishable. I can assume all the balls are same and all the cells are same. So to explore this case, first I'm going to define what is the meaning of a partition of a positive integer. What is the meaning of a partition of a positive integer? That means, so for example, n is equal to 4. How many different ways I can break this up into pieces such that if I add all of them, I need to get 4. So for example, this is 1, 1, 1, 1. So I can partition 4 into 4 different ones. If I add all of them, I'm getting 4. Or 1, 1, 2. That is one way of doing it. I'll add all of them. I'm getting this 4, and everything is a positive integer. And I can put 2 comma 2, and I don't care about the order. 1, 1, 2 is same as 1, 2, 1 or 2, 1, 1. So I really don't care about the order. I only care about all these numbers, and some of them should be equal to 4. These are all different partitions of 4. For example, when n equals to 5, and these are all different partitions of 5. I can break into 5 ones, this, or 1, 1 and 1, 2, 2, or 1 1 3 or 2 comma 3 or 1 comma 4, or I can simply put 5 here. Of course, then I the same logic I can put 4 there. And even for 4, I think you can put 1 comma 3 as well, right? These are all different partitions of 4. So these are all different partitions of 5. That means collection of positive integers whose sum is equals to 4. This is also collection of positive integers whose sum is equals to 5. And I don't care about the order. 1 2 2 is same as 2 1 2 or 2 2 1. All are the same thing. These are all different partitions. Hope you understood what partition means. This, because this is important. Let us come to case 4a. Now cells can be empty. So let us say n equals to 2 and k equals to 3. N equals to 2 and k equals to 3. So that means you have two indistinguishable balls and three indistinguishable cells. Suppose all the cells are different, then you know from previous discussion these 6 different ways we can do this. This is 1 and 2 and 3, 4, 5 and 6. Now all the cells are same. These 3 accounts to exactly same as one distribution because all the cells are same. Similarly, these 3 are same as exactly one distribution. So the number of ways you can do this is 2 different ways. That means 2 balls in one cell and leaving the 2 empty, and 1 ball in each cell and leaving 1 is empty. So there are 2 ways I can do this. If you see this, this is exactly same as I have 3 cells. I am placing 2 balls in 3 cells. That means how many ways I can split 2 balls. That means how many ways I can split number 2 into 3 or fewer parts. That means I need to find number of partitions of 2 with 3 or fewer parts. What are the partitions of 2 from the previous example? I can have 1 1, that is one partition. I can have simply 2 by itself, that is one partition. There are only 2 partitions of 2, and this partition has 2 parts in it. This partition has 1 part in it. So each thing has fewer than 2 parts. So the total 2 different partitions. So final answer is 2 for us. So this represents 1 ball in each cell, 1 comma 1, and 1 cell being empty. This partition represents 2 balls in the one cell and the other 2 cells being empty. So this is same as number of partitions of n into k or fewer parts. For example, I have in this case, I have 5 balls. I'll call that as A, and I have 3 cells. How many ways I can distribute these 5 into these 3 cells? That means I am figuring out how many different ways I can partition 5. List all the partitions of 5, which I put on the previous. These are all the 5. Each partition represents, for example, now you see how many partitions have fewer than k parts. In this case, k is 3 or k as well. So this partition has 5 parts. So this is not going to count for us. This is not going to count for us. This partition has 3 parts. This partition has 3. This partition has 2. This is 2 and this is 1. So there are 5 different ways I can do this. That means this partition represents on one cell I'm placing 1 balls, on one cell I'm placing 2 balls, on one cell I'm placing 2 balls. This is on one cell I'm placing 1, one cell I'm placing 1, I'm placing 3 balls. This tells you on one cell I'm placing 2 balls, and one cell I'm placing 3 balls, and one cell being empty. Whereas in this, I'm placing all the 5 balls in one cell and the other 2 cells being empty. So each partition will gives you different arrangement of these balls. But I have only k cells, so I need to pick out only those partitions with fewer than or equal to k parts. K or fewer parts. Okay, so in this case, there are 5 different ways I can do this, so the answer is 5. Here, I'm not interested in listing all of them. So here, that is cells can be empty. Suppose you don't want your cells to be empty. Let us look into this. Now I have 5 balls. I want to place them in 3 cells. Now I don't want any cell to be empty. So list down all the partitions of 5. This is not going to work because we have only 3 cells. So it means 5 cells, this tells you. And this has 4 cells. It is not going to work.
This will work because I'm placing one ball in one cell, two in one, two in one. This will work. This will work. I'm placing one in one, three in the other. This will not work because I'm placing two cells in one, two balls in one cell, three balls in one cell, and I'm leaving one cell empty. Even this will not work because one in one, four in one cell, and one cell I'm leaving. This is also will not work. So there are only two ways I can do this. That means I'm simply looking at the number of partitions of n, which has exactly k parts. So the answer in this case is 2. So when n is 2 and k is 3, there are more cells than the balls. I cannot do this because at least one of the cell is going to be empty. So always your n has to be greater than or equal to k. So case 4 is comparatively straightforward. Case 1 is very straightforward. Case 2 you need to do a little bit of work. Case 3, though it is a little bit crazy, but you have the formula, so you can use it without using much of our brain. So just to recap everything, and this is the bigger table which tells you all the formulas and all the cases. So again, this table is there on page 54 on your textbook. So case 1a, the formula is this. Case 1b, the formula is this. Case 2a, the formula is this. So I will try to provide one or two examples in another 5-minute video if possible, and I will do that later. So at this point, I think the video has become too long, so I'll stop sharing and I'm going to save this. Now I'm going to stop the recording.